In the last video about electrons, I came up short in answering the question, what is the ground state energy of an electron? Well, I found the answer. The answer is 13.6 electron volts. Where does that come from? Well, my research shows that it is not an easy answer. But in this series or this playlist about In Search of a Quark, if we can answer that question, if we can come up with the origin or the justification for that 13.6 electron volts, which is the energy gained by 13.6 volts across an electron, or the energy that's picked up across that point, then we can answer some of these other questions about quantum mechanics. So I'm going to do this backwards. We're going to look at the 13.6 electron volts and look at some of the relationships that describe it, and then we'll go backwards through quantum mechanics to see where all that comes from. Where do we start with this? Hydrogen atom is composed of a positive proton and a negative electron. And unlike charges attract, so there must be a force between these two. And that force is defined by Coulomb's law. And as these two charges move apart, that force becomes weaker and weaker and weaker and weaker. So that sounds like that's pretty easy. There is some really strange thing, though, is that the electron doesn't combine with the proton and then cancel everything out, at least cancel out the charge. They are equal in charge. The charge on the electron, the charge on the proton are the same. So we're going to start by trying to define what this electrostatic potential is. There's a difference between force and potential. We're going to bring that stuff out to try to figure out where we're going. I did some scratching on this little pad here to see if I can reason through some of this stuff. Here's the force between a couple charges. Q1 and Q2 is the letters I'm using. And Coulomb's law says that they are, notice here in the denominator, here's the distance between those two charges. As the distance increases, since it's in the denominator, that'll reduce the force. Now, what has this got to do with energy? It was the ground state energy that we're after. Well, let's look at an energy that is fairly simple to figure out. Potential energy. Potential energy equals the work done by a force over a distance. In other words, you move a little bit over a certain distance and you're doing work. Well, but that's not in a form we can deal with. Here's another form that we can deal with is, notice this K up here. There's some kind of constant that matches up, turns this stuff into a newtons over here. Then let's go and look at this thing. If I add up all the distances, see this little dr? This little dr relates to the r squared down here that's changing. If we add up all these distances over a range, then if we can figure out how to perform this weird process called integration, it comes up with this value right here. The E squared is the same because those are charges and those aren't changing. So I guess I don't want to confuse you there. This E squared is the fundamental charge, which one of these would be a proton, one would be an electron. So I just plugged in an E down here. Now, this constant is constant, so these two things come out. Well, how come this R squared turned into a negative R? Well, the integration rule says that you add one to this. So how come it's down here? Well, its exponent really is r to the minus 2. You add 1 to minus 2, that gives you minus 1. So that's down here in the denominator. And the negative 1 goes out in front. Negative 1, negative 1. That's why this is negative k, and this was just a positive k up here. Let's keep going. The constant happens to be equal to 1 over 4 pi e to the 0. Now, it's not an e, that's an epsilon, so that's not the fundamental charge. That's epsilon, which is the permittivity of free space in a vacuum. Whoa, what in the heck is that all about? This 4 pi comes from the fact that this is anyway, let's get to that later. I don't have a good way of explaining that makes sense right now. So let's just go ahead and leave that constant the way it is. Now the total energy, which is what we want, is going to equal the kinetic energy plus the potential energy. And one way of specifying the kinetic energy is momentum squared over 2m. And this little e comes along for the ride because it's the mass of an electron. So those two things together look pretty easy. But how do we relate that to the system of energies that all go up in a different fashion? Here's the final formula that we come to. Well, how does momentum and Planck's constant relate together? What we need to do is figure out where this comes from. Who thought this up, or how does this make sense? And we'll find that we get really close to some of the origins of quantum mechanics. I've opened up a new screen here, and these two things are copied over from the last screen. Now, who loves algebra? That's what's coming up next is algebra. So let me talk through this so that you can follow along. This a sub 0 squared is in the denominator. So the things that are in this denominator are going to shift up to the numerator, and the things that are in the numerator will remain in the denominator. Okay, let's see what remains there. Okay, 4 pi epsilon 0, that should be epsilon sub 0, h squared. So we have h squared, but remember, all this stuff is squared. So h squared squared is h to the fourth. Me is still in the denominator. That didn't change because this me actually comes up into the numerator. Let's follow that along. The 4 pi epsilon 0 squared would become 16 pi epsilon 0 squared. Here's the 2, and that makes it 32. So let's see, do we have everything in the denominator matched out there? That e sub 0 is squared. Okay? Now, the me is in the numerator now as me squared. The e squared is e squared squared, which is e to the fourth, and we've still got the h bar squared there. So that's my first transformation into all this. Now we've got to simplify stuff. Okay, h squared over h to the fourth. These cancel out. I've got h squared down here. Me squared over me just leaves m sub e in the numerator. E to the fourth, well, there's nothing to cancel out with e to the fourth. And let's see, what else do we have here? Me, I think we covered that one. Now, let's see what else we can cancel out. Uh, Me, let's see. 32 is, oh, let's go over here. 4 pi squared, where did that come from? Well, h squared is actually h bar squared is h over 2 pi. So I've got a 2 pi squared down here, and that goes up into the numerator, 4 pi squared. And let's see, what else happens? I notice I took off the h bar here because I took the 2 pi. 32 pi squared e sub 0. And I've got 4 pi squared. So these things cancel out to give me just 8 in the denominator, h squared e sub 0 squared. Look at that up on the screen here for a little while so you can see what happened to all that. Okay, looking down here, this is brought over from the last screen. Now, this little line here doesn't mean anything. That's just a mistake. Here are values for each of these different things. Here's the permittivity of free space. Notice these numbers get really crazy. 8.845 times 10 to the minus 2. Here is the charge on an electron. And I guess you could put a minus sign out there because it's actually a negative charge anyway, that's the charge on it. H is Planck's constant. Notice how small that is, 10 to the minus 34, which kind of gives you an idea that in quantum mechanics, things are really, really, really tiny, because this was only discovered when they started delving into the atom. And then mass of an electron. And this would be in kilograms, would be the natural. Notice I didn't put all the units on here, so sorry about that. Anyway, let's start plugging in values. Here's mass of an electron. This value comes over here, and the charge on an electron is this 1.602. This comes over here, and that's raised to the fourth power. Down here, the Planck's constant, 6.626 times 10 to the minus 34. And then the 8 is just in there, doesn't really. Here's the permittivity of free space, which happens to get squared. And then here's all these numbers multiplied together. And just to prove that this is true, I'm going to go to another screen that does these step by step as far as the arithmetic goes. In mechanics, things are really, really, really tiny, because this was only discovered when they started delving into the atom. And then mass of an electron. And this would be in kilograms, would be the natural. Notice I didn't put all the units on here, so sorry about that. Anyway, let's start plugging in values. Here's mass of an electron. This value comes over here, and the charge on an electron is this 1.602. This comes over here, and that's raised to the fourth power. Down here, the Planck's constant, 6.626 times 10 to the minus 34. And then the 8 is just in there, doesn't really. Here's the permittivity of free space, which happens to get squared. And then here's all these numbers multiplied together. And just to prove that this is true, I'm going to go to another screen that does these step by step as far as the arithmetic goes. All right, finally, if you multiply these two numbers together, you get 59.992, and you multiply that times 10 to the minus 107. That is the, if you add these two things together, minus 31 and minus 76, you get minus 107. And let's see what we've got going on here. This is where did the 43 come from? The 43 must have come from, let's see. Anyway, somehow we got the 43 here. 43.906. Let's go back to that other screen and find out where this 43.906 came from. 43.906 came from squaring 6.626. And the 6.586 came from raising that to the fourth power. 9 times 6 gave us this value, the 59.992. The 43.906 times 78.39 gave us 27,534 times 10 to the, and then these two are added together, 10 to the minus 92. Then let's see what happens here. If we take all these values together, when you do this division with a 10 to the power down here, the exponents actually take the difference of those, so that becomes a plus 92. So if you took a minus 107 plus 92, that'll give you a minus 15. And then these numbers, you take 59.992 and divide by 27,534. You get this 0.002178. And finally, what I'm doing here is moving this decimal point over here, which is going to change this exponent by 3. So I get 2.178 times 10 to the minus 18 joules. 1 joule equals 6.242 times 10 to the 18 electron volts, and there's the 13.6 electron volts. All I've done with all of this stuff is to prove the math so that you could go through it and prove it to yourself, just like I did to prove it to myself. I don't know about you, but I'm confused. There were an awful lot of numbers there. What is the point of moving on if we don't know what we're going to be looking for? Well, I think that the next step is to look at some basics of quantum mechanics, or at least what is quantum mechanics? Why is it there? What's it for? So, again, like I mentioned, we're going to work backwards. We're going to work backwards from some of these relationships and see where they came from, and then slowly, we'll work our way into the, I guess the best way to describe this is I just wanted to get something on YouTube so that everyone can look at it and hopefully give me some comments and help me out. And then we'll move on to some other parts of this challenge. And believe me, this is a challenge. Remember, I said this thing in search of a quark? Well, went down the rabbit hole, I guess, this time. So, anyway, hope you can watch my next video. It'll probably be a lot better.